Thank you for the introduction. Today I'm going to talk about the Gaussian Minkowski problem, and this is joint work with Huang, Yong, and Zhao Yiming. The classical Minkowski problem asks to construct a convex body whose surface area measure is pre-given. About the surface area measure, there are many approaches to introduce it. And what I would like to do is to use the variational formula. It means that the volume of the K plus TL is differentiable at 0, and the differential defines the measure of a sphere. And here the plus means the traditional Minkowski sum. And K and L are convex bodies. And HL means the support function. Support function describes the distance from the origin to the hyperplane, support hyperplane, vertical to L. All right. There are many mathematicians have contribution on this problem, and generally, we can define in this approach, in the variational approach, to define a series area measures. And let me start from this point. About 1840, Steiner found that the volume of K plus TB is a polynomial, and B here means a unit ball. And these polynomials, the coefficients of this polynomial defines Kerr-Metz integrals. Although there are many other approaches to introduce this geometric quantity, and especially W naught is volume, and W1 will be the surface area of a convex body K up to a constant. And the idea of Hausdorff in about 1930s is that this quantity is differentiable, and its differential defines a series of measures. We call it the mixed area measures, or the area measures, and we write it as Sj. When J is n-1, it's just a surface area measure, as we know. In convex geometry, we prefer the language of measures rather than the curvatures. And for instance, if K is a convex polytope, and as we can see in this picture, V1 and V2 are the VI will be the outer normal of each face, and if the area of the face vertical to VI is AI, then the surface area measure will be a discrete measure, and this is focused on the directions. The direction will be the outer normals, and the mass focused on, concentrated on this direction will be the area of the face. So this is why we call it the surface area measure. And in the high-dimensional case, for example, the R3, the Sj will describe other interesting geometric informations. I mean, for the polytope, the S1K will describe some information about the length of the edges and the angles between two adjoint faces. That's the geometric explanation, part of the explanation of these measures. Generally, for this Sj measure, the problem, or the Minkowski problem for these Sj measures are called the Christoffel-Minkowski problem. In difference geometry, and there is a connection to the PDE, is that if we assume the convex body K is convex is strictly convex and smooth enough. The support function will be written can be written in this form. It's a function on a sphere, but it can be written as v dot x. Dot means the inner product, and x is a reverse Gauss map. Then we can compute the inverse begotten map as this. So it follows that the eigenvalues of this map will be the principal radius. So if you denote the sigma k to be the elementary symmetric function, then the Christoffel-Minkowski problem will be asked to solve the following PDE. And especially if k is n-1, this one will be the determinant, and it becomes the modern pair equation, and this is a classical Minkowski problem. And for the general case, I mean the Christoffel-Minkowski problem, Fiery have considered the case J is 1, and Schneider considered the polytope case also for J is 1. And the general case, Guan and Ma studied this PDE after some regularity assumption. I mean, they suppose the given data is convex or concave, maybe to the power of 1 over k is concave, right? And Gould, Minkowski, Askina have studied also the general case, general Christoffel-Minkowski problem. All right, so it's very natural to consider a general Minkowski problem for a general geometric measure. As we can see, the measures before all have some geometric explanations. They will describe some special geometric information. And if we can define some measure to describe some geometric information, and there will be a general Minkowski problem for them. That means given a measure mu, it asks to construct a convex body whose measure mk is mu. And some measures, some well-known measures are the curvature measures and Arsendoff integral curvature and the LP surface area measures, and which was defined by Luttwak in 1993 and solved by Zhao and Huang. And in Zhao Wang's paper, they also find an important case is that the P is equals to -n. It's called the central affine Minkowski problem. Another important case is case P0. In this case, the measure LP surface area measure will be called the cone volume measure. And Stanko have studied the case in dimension 2. And Brodsky, Luttwak, Yong, and Zhao completely solved the symmetric case. Yeah, and Zhu considered the discrete case. A recent study, a discovery, is that the Huang, Luttwak, Yang, and Zhang found that the dual curve mass integral is also differentiable in some sense. And this differential defines the dual curvature measures. It's remarkable that there are many other geometric explanations rather than the variational formula here. So the differentiable here means that if we define the Wolf shape as given a function h, we can define the Wolf shape by the intersection of the hyper subspaces. No, the half subspaces, intersection of the half subspaces generated by h, and let ht be the log family, and then the dual curve mass integral of the Wolf shape is differentiable, and this differential defines the so-called dual curvature measures. And for the case Q belongs to 0 to n, they HLZ themselves partly solved the problem. And in the paper of Brodsky, Huang, and Poland, they found an optimal necessary condition. And under this condition, for the integer case, Zhao solved it, and finally completely solved it. I mean, the even measure case, the 5 others solved the case for the Q belongs to 0 to 1 and even measures, and under the optimal condition provided in this paper. And Huang Poland also studied the case for Q is larger than in the necessary condition, and Wang considered the flow. I mean, they use a PDE method to study relative problems. Okay. When Q is smaller than 0, Zhao studied, and this also can be found in Wang's paper. The Gaussian image problem may not be contained in the dual Minkowski problem, but it is quite it has a close relationship between the extendable problem. I mean, the Q is 0 case will be the extendable problem. So I put it here. So now we turn to introduce our problem. An important thing to note is that the method, the technical developed in HLY's paper is that when they proved that variational formula, they developed some technicals, and these techniques can be easily applied to many other quantities. So we can try to find other maybe interesting geometric measures. And we will focus on the Gaussian measure, and we will say the Gaussian measure of a convex body to be the Gaussian volume. And actually, the study of this measure and on convex geometry, there are many related studies, and I just posted part of them here. Some of them studied the hard inequality. That's a type of Brown-Minkowski, Gaussian Brown-Minkowski inequality. And other guys studied the Gaussian correlation conjecture, and it was solved by Roy. And Garden Zavich in about 10 years ago, they posed a very interesting conjecture, another Gaussian Brown-Minkowski type inequality. And in recent years, it was solved. Based on this, many colleagues have studied this conjecture. I mean, okay. As we mentioned before, the technicals in HLZ's paper can be applied to differentiate this one, and actually it works, and it defines the measure as gamma and k. It's not quite a surprise. And actually, this measure was considered before, but not from the variational method. And Lipschitz have studied some parametric inequalities for some general measures, including this measure, but they are not studying the Minkowski problem from this approach. And Garden, Hug, Will, Xing, and Ye also studied the Orlich Minkowski problem, and they defined the general volumes. And if the function g in their paper are chosen to be some special function, they can also recover this measure. But it seems that there is no one to focus on the Gaussian Minkowski problem. and we can formulate our problem here as this. That is, give a finite barometer Minkowski sphere, can you find a Cox body such that the Gaussian surface area measure S gamma n k equals to mu? And if there is a solution, is such a solution unique? There are two problems. And in the smooth setting, as we introduced before, it asks to solve the following PDE. And here is determinant, except this, there is exponential here. And because of this term, this guy will be not homogeneous, and something will happen, and we will see it later, some difficulty things. All right. Another point to consider the Gaussian Minkowski problem is that, as recall in the classical Brown-Minkowski theory, there is a quite close relationship between the Brown-Minkowski type inequalities and the Minkowski problems. And these two guys are very fundamental things in the Brown-Minkowski theory, I think. Actually, if we have in the classical setting, we have the classical Brown-Minkowski inequality, then we will get the uniqueness of the solution of the Minkowski problem. That is because of the homogeneity, right, in the classical setting. And an interesting thing is that there are also many mathematicians have considered the Gaussian Brown-Minkowski type inequalities. And the first one is the unhard inequality. It reads as this: phi inverse gamma n is concave. It can be written as this. Phi inverse here means the primitive of the Gaussian density. Phi x is this, and phi inverse is the inverse function of phi. And the other type of Gaussian Brown-Minkowski inequality is the Garden-Zawich's conjecture in 2010. They conjecture that for symmetry convex bodies, the gamma n to power 1 over n is concave, and it was recently confirmed by Akinakis and Moshidis, and their work was combining with was based on the also. Okay, I mean you need to combining with their work with Korennikov and Levitch's work, and to confirm this conjecture. It was a story that this is actually an important point to stimulate us to consider the Gaussian Minkowski problem. Because that, as we mentioned before, for the classical Brown-Minkowski type inequalities and the area measures, here is the SJK, and Hausdorff have an approach to differentiate the Brown-Minkowski inequality, because the Brown-Minkowski inequality describes the concavity, and we can differentiate to get some Minkowski type inequality, and then we will get he could get the uniqueness of this measure, the SJ measures. So since they have proved this conjecture, so it's very natural to consider if we can differentiate the Gaussian Brown-Minkowski inequality to get the uniqueness. And we try differentiating the Gaussian Brown-Minkowski inequality. Actually, each inequality works. We can obtain the following type, Minkowski type inequality, and there is equality cases. But we cannot derive from this inequality that derives the uniqueness from this inequality because of the lack of homogeneity. And actually, if you do it carefully, and if we have, in addition, this equation, I mean the gamma nk equals to gamma L, then if two convex bodies have the same measure, Gaussian surface measure, then K and L must be the same. So the point is that we cannot directly obtain this equation from that their measures are the same. So this is the point, and I think the main point, main reason may be that this one is not homogeneous, and this inequalities is also not. But if we look at this one, it's almost homogeneous. Almost homogeneous. Why we say this? Because it's a phi inverse, and the gamma n is the Gaussian, and the phi x is the primitive of the Gaussian, and the phi inverse here, it looks like homogeneous. I mean, so we try the Earhart inequality, and it's very lucky that after some computation, we will have this one. If K and L have the same measure, we will have an inequality written in this form. And after a careful examination, we can find that the psi prime and psi are strictly increasing if the variable is larger than 1 or 2. So this means that if in this setting, if we assume gamma nk, gamma L is larger than 1 over 2, then we will have gamma nk equals to gamma L if they have the same measure. And by this inequality, we will have the k must be equals to L. This is a partly uniqueness result. And its proof is not hard, but it's very lucky to see this. And it's a start point is the solution of the Gaussian from Minkowski inequality conjecture, but we finally didn't use it. It's very interesting part. And after uniqueness, okay, let's summarize the uniqueness here. That is, if K and L are in this set, and then the same measure implies the same body. And in general, if without this setting, the uniqueness will not be true. Yeah, because even for the constant solution, I mean, if you see the balls with radius r, then the density of the measure will be this guy, and this guy equals to c. We always have, in many cases, we have two solutions, and we don't know the constant that implies a constant solution. We only know, what we know is that under this assumption, it's unique, the solution is unique, right? So for the existence of the problem, that means given a mu, try to find the S gamma and K, try to find the corresponding K such that the mu equals to S gamma and K. This is an existence problem. We have the first result is from the variational argument. This is very useful technical in Clark's geometry. And we can consider the optimization problem or similar problems. But since we don't have the homogeneity after the variation, after the using of variational formula, there will always be a constant left in the solution. So the first result is reads like this: mu equals to S gamma and K over a constant, and we cannot remove it. But somehow, let's recall that we have the uniqueness in some assumption. I mean, if we assume the gamma and K is larger than over 2, we have the uniqueness. So maybe we can try to use some method in the PDE, for example, the method of continuity or the degree theory. So our main result about the existence part is to use the strategy developed by Li Yanyan in 1989. And we will look at the even case. I mean, the given matter mu is even, and we try to find the symmetric convex bodies. And our result reads like this. If F belongs to C2 alpha and is even, and its total mass is smaller than 1 over square 2 pi, this condition is to provide our final assumption will satisfy this inequality. That means satisfies the gamma n case larger than 1 or 2. And under this assumption, we will find a unique C4 alpha convex body such that the equation holds, right? And after an approximation argument, we will have the solution for the even measures. If the mu is even measure on Sn-1 and the total mass is smaller than 1 over square root 2 pi, then we will find the solution. And we will find the solution satisfying the gamma n case larger than a half, and it's unique under this assumption. And this one solves mu and without any constant. This is it solves our original problem, right? So let me see if I have 10 minutes. All right. So in our solution, we will consider this equation, and we assume there is constant such that the C2 alpha norm of the data F is controlled by the constant C. We also assume that the total mass of F is smaller than 1 over square root 2 pi. This is I have explained it. This is to by using the Gaussian isoperimetric inequality mentioned before. This condition will provide that the solution, the Gaussian measure of the solution convex body is larger than 1/2. And the strategy of the degree theory is that if G is continuous on the product space, 0, 1 times Sn-1 times R times R n-1 times R n-1 square, and we define the GT, the capital GT, to be an operator from C4 alpha to C2 alpha. It's a traditional way to define an operator in PDE. And that if O is a bounded open subset of C4 alpha, and if GT satisfies the following three conditions, that is, the first, GT is uniformly elliptic on O, and GT is continuous in T, and the third one is GTH equal to 0 has no solution on the boundary of O. Then we can define the degree GT, and this guy will be homotopy invariant, and this means that degree G0 will be degree G1. And this is a strategy developed in Li's paper, 1989. And in his paper, he also provided some computation method of the degree of some special operator. And And another important fact is a non-zero degree will imply the existence of a solution. That means if the degree, you can compute the degree is not zero, then you will find, it means that there is a solution of this guy, GH is 0. Okay. In our case, we will look at the FTH. And the FTH defined by this minus this guy times FT. And FT is the convex combination of C0 and the TF and F. And C0 is a constant. And we can choose the C0 to satisfy that FT always satisfy these conditions. It is easy to achieve because of the convexity of the norms, right? All right, and our main lemma is to do the a priori estimates. That means there exists a constant C prime, only depends on the constant C, such that if H is a solution of Ft and gamma H is larger than 1 over 2, then we will have the C4 alpha estimates. And the third one will imply that it is the Ft is uniformly elliptic, right? And after this estimates, we can define the bounded open set all by this. And these conditions, in these conditions, the C prime is obtained from the estimates, and the last one is our setting to provide the uniqueness, right? And it's by the estimates before a priori estimate. Ft is obviously continuous in T, and it's easy to check the uniform ellipticity. And what we need to do is to show is that the important thing is the third thing. There's no solution on the boundary, and this why to provide and only after this one we can define the degree on O. All right, and to prove this, if H is a solution, then by the estimate we have this one, and by our inequality. All right, if H is on the boundary, by the estimates, it finds all the conditions, all the three conditions. But if it's on the boundary, it must happen. It can happen only if the gamma H is one half. Gamma H here means gamma, the wolf shape of H, right? And the Gaussian S-parametric inequality we obtained in the previous pages will imply that the total mass of the area, Gaussian surface area, will be larger than 1 over square root 2 pi. So this assumption in our data F will provide that this is impossible, because if FH is the solution, we must have this one, the solution of FT, and FT satisfies this. This is a contradiction. So this proves the step 1. And after step 1, we will have the degree definition. Degree will be well defined, and we will have the homotopy invariance. And the step 2 is compute this guy. And note that in 0 case, F0 is the C0 is a constant. F0 is defined, can be find here, sorry, here. When T0, Ft will be constant C0, and in this case, by using the theorem in this paper and the uniqueness result and the chosen of C0, we will compute the F0H the degree of f0 s will not be 0. All right, that's the final step. And yeah,